Please go ahead.
Okay. So thank you, Julio and the whole Galvani Consortium for inviting me and giving me the possibility to present part of my research here. I have to apologize to the neuroelectrics people because I gave a very similar talk a couple of weeks ago in the context of our NeuroTwin European project. But I thought that it's really very relevant for the Galvani people, and therefore I decided really to go to a very similar take-home message. Nevertheless, I included, in order not to bore you, some new concepts and some new results. So the main idea of the talk is really to present a new methodology. It's a methodological talk, basically, where we try to infer a hierarchy or information about the underlying causal interactions at the functional levels by assessing the arrow of time. This is the main take-home message. So let me try to motivate that. So we are nowadays, and actually not nowadays, since many years, interested in hierarchical organization. And as you know, the huge interest in hierarchical organization, most of the papers on hierarchical organization are really restricted to anatomical facts, which are extremely interested, and is probably the basis of the hierarchical organization at the functional level. But as you can imagine, I mean, anatomy is pretty fixed, and function is not so fixed. So it's much richer, and it's very different. And in fact, there are not so many studies on the hierarchical organization at the functional level. And it's extremely relevant for us because we want to see in which way the hierarchy of this functional organization change under different brain states, if you are conscious, if you are unconscious, or under different cognitive state, because that will give us a very concrete computational idea on how the brain orchestrates cognition in general. This is the overall motivation and an idea. Well, in order to assess the hierarchy, I mean, then there is no way. I mean, you have first to access this functional interaction, and this is probably the reason why there were until now not so many studies on functional organization, because to access the underlying functional interaction, the causal interactions at the whole brain level, is not so easy, as you know. There are many methodologies. I will present some coming from our group, for example, at the very beginning. But as you can imagine, you have to start. I mean, if you use just correlation, it's not so good. It's not good enough. It's very simple. And you can access some level of coupling functional interaction, but it's probably not so informative for assessing really the whole hierarchical organization. Then you have, or you are obliged to use more sophisticated methods, and that means that probably then it's time consuming, and you need a huge amount of that. Classical example, for example, Grange causality, and I will show you just an example in a couple of slides. So therefore, the main idea here is really to do the same, but in a different way. So to try to assess these hierarchical organizations, to get some information about the underlying causal interaction without measuring that directly. So it's an indirect way of having information about that. And the trick is extremely simple. And then I can mention that and stop. I will go for the coffee pause. I mean, the tricks come from the thermodynamics. It's basically associating this hierarchical organization by a measure of how asymmetrics are the underlying functional interaction. And this is what we call in thermodynamics the breaking of the detail balance. And we know in the thermodynamics that the breaking of the detail balance goes hand in hand with the idea of the arrow of time, with the idea of reversibility. So what we will do is basically to assess the arrow of time in brain signals, as we saw in the title, and through that to infer something about the underlying hierarchy. This is the whole idea. At the end of my talk, I mean, if I have a little bit of time, of course, because this idea of non-equilibrium, non-reversibility, assessing or allowing us to assess the underlying hierarchy is related, or most of the time is concomitant with a very particular type of dynamics, which is the kind of spatial-temporal chaos. that we call turbulence. I will say a couple of words about turbulence because it's a very interesting extension of this concept coming from the thermodynamics, coming from non-reversibility and non-equilibrium, and it's a very valid biomarker in many contexts. But I will just mention two words about that. So just to be more concrete on the functional organization, one example of possible hierarchical functional organization, there are many, but one that was very prominent, is very prominent in the context of cognitive neuroscience, as you know, was proposed by Bars many decades ago. It's a concept of global workspace, and that was, of course, refined by Saint-Degrien and Jean-Pierre Chanchot. And the idea is just that we have different brain areas, of course, and they are functionally connected with a particular topology. In particular, the interesting point here is that there is a central core of brain areas which are really orchestrating the whole functionality. And this kind of information is what we are trying to indirectly to discuss. As I mentioned before, I mean, there are many ways of doing, well, I don't know if there are many ways. There are some ways of doing directly. This is an example. Sorry, it comes from our own lab. I mean, it's pretty recent. We just published in Nature Human Behavior. And we have done really, actually, a very simple direct approach. So we extended the Granger causality in a more information theoretical context. So it's a transfer entropy, refine it with some normalization, et cetera, use of surrogates and so on, and basically using a very large data set, which was the human connectome projects, neuroimaging, 1,000 people under many different conditions. In fact, are shown here the 7 different cognitive tasks and resting conditions, and then you can do for different parcellations this inference of the causal functional interaction under all the different conditions. If you do a kind of intersection, actually it's a little bit more refined than an intersection, then you find that really the core regions are those, or are quantitatively, basically a candidate of quantification of those global workspace regions. So this just to give you a flavor of the direct way. Now the whole talk will go the direction of the indirect way, and as I say, it was motivated by this key concept of non-equilibrium and non-reversibility that I already mentioned a couple of weeks ago. I mean, I was really during the pandemic time reading a lot, and I met that book, which I really strongly recommend, What is Life from Schrödinger, which is extremely beautiful, and actually it has a huge impact in biology because basically he was arguing that the concept of non-equilibrium and non-reversibility are absolutely relevant for the understanding of life. Another key paper was from the lab of Danny Bassett, from Christopher Lin. Also simultaneously, basically came a very similar paper from our lab, from Jonathan Sandspell. But the idea is already there. And as I mentioned you before, I mean, in thermodynamics, we know that if we have the tail balance in the brain or in an artificial system, this is actually a kind of a spin system, just nodes interacting with each other. And we know if this system is symmetric, as is very nicely shown in this cartoon, then the system is reversible in time. And there is consequently no change in the so-called production entropy. On the other hand, if we break the symmetry and we start to introduce some asymmetry in the underlying causal interaction, so we start to build up some hierarchy, then the production entropy, increase, and the system start to be non-reversible, and you can start to detect an arrow of time. And this is the key idea. In the paper of Lin and in the paper of Enzo Tagliastrucchi and Jonathan Sandspell in our group, basically the idea was to calculate directly or to assess this underlying level of breaking of the detail balance, or to assess the underlying level of hierarchy by measuring directly the entropy production. And this is a problem, to be honest with you, because you have a high dimensional space, which is your pixelation space, and you have to estimate an entropy in that space. So therefore, you do the usual dirty tricks, and you get something, but it's not the optimal. So the motivation was really to try to assess exactly the same, but directly measuring the arrow of time. The motivation is shown in these movies, if I can. These are two systems, one macroscopic system and one microscopic system. On the right, this is a spin system, some physical system, which is driven in non-equilibrium. So we know by definition, by construction, that is non-reversible. This is just a movie of Christopher Nolan, Tenet, which is a beautiful example of a macroscopic system where you have a mixture of people going forward in time or going backward in time. So it's very easy to distinguish who is going. So those guys are going backward in time, as you see, and those guys are going forward in time. So very easy to distinguish non-reversibility. This is also a non-reversible system like this, but it's at the microscopic level. And sometimes, because of the incidence of the noise, we could have problem in distinguishing what is forward and backward. In fact, what I am showing here is one of the variables describing the system, how evolving in time, but one is the forward, so the real evolution, and the other is the reverse or backward. And as I always say, I'm not doing this on purpose. I'm doing this because I don't have good memory. I generated that, and I don't remember which one is which, and I cannot say which one is which. On the other hand, we have also other systems, macroscopic in this case, that where we can distinguish very easily because they are non-reversible, or we cannot distinguish in our time because they are, of course, non-reversible, absolutely reversible. And these are the two classical examples. For example, this movie, forward and backward, it's very clear which one is the forward and backward version because it's a strong non-reversible macroscopic interaction. This is the classical elastic collision between billiard balls, which are by definition absolutely reversible, and therefore there is no arrow time. And in fact, if you see the movie forward or backward, you cannot say anything. So take-home message is that, and this is the key idea that of the methodology that I will present today, is that in order to distinguish this or to assess the arrow of time, the level of non-reversibility, instead of measuring the production entropy, which is difficult, we will assess directly the arrow of time by comparing really the two directions of how the system evolved in the forward direction, which is cartoonized here, or in the reversed backward direction. And if we see that there are differences, if we can distinguish that, and we know that that's go hand in hand, hand by hand with the underlying production entropy, but directly we have a measure of this similarity or distinguishability between the forward and the backward system. We know that, of course, in the case of signals, in our case, brain signals, that could be difficult, not because it's microscopic, but because it's, of course, contaminated with noise. So that, and this is what is reflected here, that in some cases it's very easy to distinguish the forward from the backward evolution, and in some other cases it's relatively easy existing that distinction because the system is not reversible, but it's not so easy to distinguish that. Yes.
Apologies to interrupt. I just wondered, is it important that the dynamics are symmetric in time? What if we have like a faster system and a spike and a wave, you reverse it, and the dynamics are a little different, although it is a non-equilibrium system?
You mean that I don't know if I understand properly what you think. I mean, because what we are measuring is exactly the symmetry in time, but in terms of reversing the time.
Yeah, okay.
But so it's not what you mean. Or you mean if there's many time scales, or?
I'm just thinking about other deterministic systems that are therefore non-equilibrium, but they do have asymmetries in the time domain.
Oh yeah, that is exactly what we are trying to assess. Okay. For example, you could have a pretty, I mean, actually the simulation that I was showing was a deterministic system, was a spin system that was driven
in state space. And your symmetries in state space don't have to be symmetric. No. It's important that the Markov property going forward and backward is satisfied.
Exactly.
It doesn't need symmetry.
Exactly.
like a spike,
Yeah, yeah.
as an upswing or something like that.
So that is the idea of the key idea of the methodology, that you take your favorite type of range signals. I will give you two examples, BOLT and some ECOG data. So BOLT in humans and ECOG data in monkeys. And you can do a different labels. I am only showing today, because of the time, global aspect of the dynamics, but you can do at the network level, you can do even at the node level and so on. And the key idea is whatever is your signals, in this case, let's say it's one-dimensional BOLT signal, we know the natural evolution of the signal, this is how we measure, and then we artificially flip the signal by hand. And we know that by definition, we have the backward, the reversal version. But by construction, we know who is whom, and therefore we can classify them, and depending how good we can classify on a validation set. So by looking at the performance of the classifier as a first methodology, I will present another one which is even much simpler. But just to get this idea, if we can distinguish it, that's in a very, very easy way. That means that we have this asymmetry in time, and that means that high performance is telling us that there is no equilibrium, there is no reversibility, or what is more important for us, that is a hierarchical, a rich hierarchical functional organization, because it's revealing this underlying breaking of the detail balance. If it is low, it's exactly the contrary. Just to give you a little bit more details, basically in this first step, what we do is we take the signals, we analyze the signals in a sliding window. In each sliding window, we do this procedure of forward and reversal, and then we train across all the windows and across all the subjects and trials a deep learning classifier that we call TENET, but in this case means temporal evolution deep learning classifier. And basically done by evaluating the performance of TENET on a validation set, as I said, at different levels, then we get a number, and this number is giving us the label of hierarchy or non-reversibility or non-equilibrium. It's just to give you a concrete flavor of what we get when we analyze the human connectome project data. As you know, more than 1,000 people, neuroimaging data, BOLT data, under different conditions, resting, and 7 different tasks. And each dot is a subject. And what you see is the distribution, basically, of this different level of non-equilibrium, which is revealing that under resting state condition, as somehow intuitively expected, you have non-reversibility, but it's the lowest level of non-reversibility. So it's the most simple type of hierarchy. And of course, when you start to do computations associated with the cognitive task, then you need to break the underlying symmetry, because you need to orchestrate the communication between the different involved brain areas. And that is, of course, is reflected at the level of the arrow time of those signals. Here I would, it's just how that changed across the sliding window, across times. It's also interesting to see this level of non-stationarity, but I will not comment too much on it. So this is the new part, neuroelectrics, wake up again. This is a much simpler way of doing the job. And it's fantastic, I am in love with it. Because we got rid of TENET. Because I was arguing at the beginning, well, to measure transfer entropy and so on is really, range causality is difficult. You need a lot of data, you need a lot of computation. For training deep learning networks, you need also a lot of data and you need a lot of computation. So it's conceptually beautiful, but in fact, it's not so practical. And therefore, we came to an idea which is much, much, much simpler. It's very stupid to calculate. It takes really seconds in a laptop. And it's exactly revealing the same concept. Let's concentrate on a pair. And of course, then we extend that to all possible pairs in form of mathematics. The idea is the same. I mean, just to assess the directionality in the transitions in space. which is exactly what the production entropy measured, by the way, in terms of probability. But here just at the level from the signal. And the key idea is that you take these two pairs, you shift them and calculate the shifted correlation. Okay? For a given capital T, I mean, this is for all possible capital T, but we have some methodology for selecting a good capital T. But as you can imagine, just to give you a flavor, I mean, a good methodology is that T should be really small enough. And that's it, usually works. So then you have a cheap version of the causality here between these two pairs. In the forward version, then you do exactly the same trick. You flip both signals, you measure exactly the same, the shifted correlation, and comparing, of course, at the same capital T, the two shifted correlation, you get a number, which is, of course, quantifying the label, the arrow of tan, or the level of non-reversibility, the level of non-equilibrium, the level of hierarchy. If you then extend that for all possible pairs, and you compare basically element-wise, I mean, all the matrices, I mean, of course, you get a global number, or single pair numbers that describe the whole problem.
What is FS?
On
On the right.
Oh, it's the shifted correlation.
FS shift.
Yeah.
Thank you.
Functional shifted correlation.
Sorry, so this is like cross correlation, you're looking only forward?
It's the cross correlation. It's like the cross version of the autocorrelation. Yeah. So you just shift the signals.
But you look only forward.
I look only forward in time. Yes. Yes. Indirectly, I look backward in time when I do the reverse. Okay, just to see how that works, we took this public data from the NeuroTyco site. I mean, there are, in this case, 4 monkeys. They were implanted with ECOG in half hemisphere. And it's a beautiful, really, data set because you have many different conditions, also cognitive conditions. In this case, I am just showing the conditions revealing different level of consciousness. For example, one condition is comparing awake with sleep, or the other condition is comparing awake with different anestheticum, propofol, ketamine, and so on, and the recovery, which is also very, very useful to see. And what you see here, basically the most important information is here. So for all these conditions, awake, sleep, awake, propofol, recovery, awake, MD, recovery, and so on, what you see is the global level of non-reversibility associated with this shifted correlation matrices differences, and then you see very clearly and significant differences, and going in the right direction. That's when you get unconscious, there is less breaking of the detail balance, meaning that the hierarchical organization, the functional hierarchical organization is flattening, which is what we expect. When you are awake, of course, there are more interactions, more asymmetric interaction, and that is what happens. The only exception is ketamine, which is fun. That's probably the reason why ketamine is an entertainment drug nowadays. You get high, I mean, you get more structured. I don't think that's in the right way, but anyway. So these are just single examples for particular monkeys, particular trials where you see the evolution in time of those values. And this is just a functional connectivity, just which is expected. I mean, it's just a cosmetic effect for the paper. That, of course, I mean, you cannot get the inference of the underlying in the underlying hierarchy by just functional information. Just to finish, I mean, as I mentioned at the beginning, I mean, most of the systems that are out of the equilibrium and are high dimensional, for example, hydrodynamic system, in a concomitant way, you have a particular dynamical state, which is associated with what we call turbulence, for example, in the dynamic context. I always mention, because for me it was very astonishing. I mean, the word turbulenza was first introduced in Italian by Leonardo da Vinci. And it's very interesting. We even wrote a paper with a specialist on Leonardo da Vinci about that, because he was genuinely really interested on on this mixture between order and disorder. And this is what he was trying to capture in his drawing, because he realized it immediately that when you have a turbulent regime in water, for example, then some parts looks really very stochastic, and some other parts look extremely structured in the sense that you see the emergence of those different vortices. And even he analyzed the relationship between the vortices and so on. So this is just a movie, a cartoon movie showing how people then during the centuries after Leonardo da Vinci really tried to study this crowding movement. I forgot to say turbulenza comes from turba in Latin, which is a crowding movement. And the first observation that was extremely useful, and it's extremely useful for us, was done by this guy, Louis Richardson. That's expressed in a poetic way that I will repeat here, was an observation that was already done by Leonardo and even wrote down, that the size of the vortices are somehow hierarchically organized. You have all possible size, and they reflect apparently, this is what was expressed in this poem of Richardson, a hierarchical organization, which makes a lot of sense, because in hydrodynamic, what you have is kinetic energy, so velocity, and to transmit the velocity to the next size vortex makes a lot of sense in terms of efficiency. Of course, you need a genius like Kolmogorov that came to that idea and say, oh, what those people were observing on sure is efficient transmission of energy and information. Oh, no, now we are also interested in that, because in the brain, we need exactly the same. I mean, a good transmission of information across space and time, and therefore this idea coming from the non-equilibrium idea could be extremely useful for us. In fact, Kolmogorov introduced a concept that is called structure functions, which has nothing to do with what we call a structure of functions in neuroscience. But if you see, it's just the quadratic differences between the value of your variable. For him was velocity, for us will be brain signals, or whatever, separated in a Euclidean distance R. And in fact, if you develop that, then the main or the core of this definition is just the functional connectivity. It's what we call functional connectivity, just the correlation between the signals in two different positions. The only accent or the only nuance here is that instead of taking just in two different parcels, in two different nodes, we take into account, or he was very much interested in how this functional connectivity or correlation evolved as a function of the distance. Why? Because he was interested exactly in the transmission of this correlation information across the distance. In fact, I mean, it's shown those cartoons by Kolmogorov, and that has a huge influence in the theory of turbulence. He was able to show that there is a range called nowadays the inertial subrange, where energy and information in terms of structure function of correlation show a power law, and this power law is a direct quantification of this idea of Leonardo da Vinci and Richardson, that is associated with the hierarchical organization of the vortices. Okay, how we use that? I'm missing transparency. Okay, sorry. 5 minutes. Yes, I am practically. Just how we can use all these ideas, which intuitively are interesting because they are talking about efficient transmission of information across space, time, blah, 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 in the context of neuroscience. So we don't have water here. We have blood, but well, maybe we have water. But probably it's not so relevant for our process. And there is a way of doing that, which is based on the theory of oscillators of Kuramoto. And it's actually extending a concept that we are using all the time in neuroscience. And the concept, and it was a slide that was missing, the concept of Kuramoto order parameter. Kuramoto order parameter, as you know, is basically for each node, in this case, is continuous, therefore it's the sum over all the nodes. So the integral in this case of the exponential part of the imaginary of the phases. And you know that the module of that, here is R, is a number between 0 and 1. 0 means no synchronization, 1 means absolute synchronization. And we use this all the time. Actually, we use an extension, a cosine of that, which is instead of looking just at the mean value across time, which is the synchronization, we look at the standard deviation across time, which is what we call wrongly metastability. And it's nice because it's describing how rich is your dynamics, so how much your level of synchronization is changing across time. So the key idea here is that he extended the idea of Kuramoto order parameter to include this locality. The locality is introduced by this extra kernel, which is an exponential kernel. And basically what you have here in the module of this is exactly the same, but in a spatio-temporal term. In the global Kuramoto order parameter, you have only the time because we are summing up over everything. Here, you are summing up over everything, but in a weighted way. So therefore, you have the dependence on X. In fact, if you study this in a system of couple oscillator, and you plot here in color the label of local synchronization, what you see is that across space and across time, you have a huge variability under certain circumstances. And this huge variability is what we call turbulence. Or if you don't want to talk about turbulence, because some people get scared about the semantic of turbulence, you say, I don't care. This is the spatio-temporal extension of the concept of metastability. So I look at the richness of the dynamical repertoire, a word that we use a lot with historically with Victor, but now in a spatio-temporal sense. Okay, now I just show again for the HCP with a very fine parcellation, just as this value. So the standard deviation across space-time of the local Kuramoto order parameter, so this spatio-temporal extension of the concept of metastability is high. And that means that the system is not only non-equilibrium, it's not only non-reversible, but it's also in a turbulent state. In fact, I mean, this is just a snapshot of the phases for the surrogates and for the particular subset of the HCP data set. And you see here for all these nodes, 1,000 nodes in the Sheffer parcellation, the phases are clustered, and this clustering is changing across time, and the cluster is changing across space. And this is exactly a very beautiful way of seeing this very particular dynamical regime that we call turbulent. This is just a movie of that, I mean, rendered on the brain for a particular subject, the difference level of local synchronization, which is, again, revealing explicitly this vorticity. This vortex is the level of local synchronization, and exactly the same, you can see that in the brain, and you can model and so on. Just to finish that, I mean, this is an excellent biomarker. Of course, I mean, metastability, the classical metastability, we knew that was a very good biomarker of brain states, disease, and so on. It's just to give you a flavor of the turbulence. There are other biomarkers, but forget them. That's the level of turbulence and the different state of consciousness. This is coma. This is a sleep, wake against deep sleep, or even under meditation, no meditation, then you have a significant reduction of the metastability, of the spatial-temporal stability, or the spatial, or the level of turbulence. You can do this at the network level, and it's also very beautiful to see that under different manipulation of consciousness, even here including psychedelics, but here you are under different level of unconsciousness, deep sleep and deep coma or minimal consciousness. And even if behavioral is the same, dynamically it's very different. You have a kind of fingerprint of the level of turbulence in all these conditions. So I finish here. I think the take-home message is that of this methodology that allow us to see this level of non-equilibrium, non-reversibility, not because non-equilibrium is interesting per se, actually, non-equilibrium, I don't think it's interesting per se, but it's indirectly or directly interesting because it's indirectly characterizing something that is absolutely relevant for us, which is the label of hierarchical interaction. I finish.
Questions?
So you made the link between reversibility or not and the Kuromoto model, which is non-locally oscillators. I wondered, does it fit in the same way with the edge of bifurcation noise model as well? Have you looked to see whether this, or does that really produce reversible?
Yeah, it's a very good question. And we have the same intuition.
Yeah.
Because also, actually, with Victor, we were doing in our young days a lot of these manipulations, claiming that the best model of the brain is at the edge of the bifurcation and so on. We were able to model that exactly with the same type of model that we were using before at the edge of the bifurcation and so on. And we get, again, a very good fitting of the level of turbulence and so on. And therefore, for me, practically it was intuitive to say, well, should be the same. So the turbulent regime should be a particular dynamical regime appearing at some edge of whatever bifurcation. I started to look in the literature. There are practically 2 papers in the serious turbulence literature relating bifurcation theory with turbulence. So we don't know. It's the answer. My belief, basically, I think we are near by causality than most of the people in standard turbulence theory, because we have already a demonstration that we have a model, exactly the same model, which is a Hopf model, it's an oscillatory model, couple of oscillators, that we know has its own characteristic of turbulence, and we know its own characteristic to be at the edge of a bifurcation. So for me, the answer would be yes, but I cannot claim that because I don't have a sort of demonstration.
Somehow it's a different scale. So the coupled Kuromoto oscillators are like a small scale Hopf model. So the coupled Kuromoto oscillators could be approximated by the Hopf model. So I don't know, you might get this irreversibility washed out in some sense of the Hopf model. But I guess we see.
Yeah, it's a long discussion. but excellent point there. Yeah, you have a level of irreversibility already in the model per se. Yeah. And then but the beauty is that you can adjust the per se level of non-reversibility of the model according to the level of the non-reversibility of the data. And that's provide you with extra information. But it is another talk.
Good. Thank you for this very nice talk. I really enjoyed it. It's not my field of research, but no, my question is, would you say that an epileptic seizure is a turbulence or not a turbulence in the brain?
Beautiful question. We speculate about that. The problem is that this beautiful question is linked with a very hard methodological problem, and is to measure or to quantify turbulence, you need really very fine, spatially fine description of the dynamics. That we don't have, not even also in
even from EEG.
Even from EEG. But you can define another measure, and we define it, which uses a single trick, and instead of doing this kernel of the local Kuramoto, we go again to the I mean, when you don't have a solution, go always to second order. It works always. We just extend it basically, and we look pairwise, the metastability, and we were showing that that is very good biomarker of turbulence in standard systems. And with this measure, then we have a chance to look at EEG.
Okay.
We are on that.
Okay.
And maybe because you said even in EEG, one definition of turbulence is a scaling property across space or in state space. So you have to go, in order to make a statement, you have to go over many scales, not just a few scales.
Okay.
So that's one of the reasons. Gustavo, for the reversibility in thermostatistics, when you look at this is a little technical, but it could make sense here. When you go to the Fokker-Planck equation, what is very often being used to make proofs is you compute the Fokker-Planck operator forward in time for the forward evolution, but you can also replace the time by minus t, and then you have a forward and a backward operator. And this combination thereof is very often used for proofs of certain theorems. That you have essentially a forward flowing Fokker-Planck operator and a backward flowing. Could this be a possibility to that could potentially be useful here for making some proofs and extracting some features? Because there is a whole mathematics that is behind that, addressing reversibility, irreversibility, what can be shown, what is more less demonstrative, etc.
I cannot talk with you. We have many common points. I mean, we were astonishing today during breakfast. I mean, I am thinking on that. I mean, me too. I mean, come on. Yes, of course. I mean, and we are looking at that in a very simple context, which is a spin system. The spin system, basically the Fokker-Planck version of for the spin system is the mean field, which there is a long tradition of mean field in the Ising spin system. The whole mean field tradition of Ising spins is in equilibrium. So all the systems are symmetric and balanced. I discovered that there are a couple of guys going very crazy where they developed and extended the mean field for the non-symmetric case. Actually, it's someone from Zaragoza, from Spain. It's a genius, Aguilera. So that's that I think is an easy version of that, where we can go with the mean field forward and backward, which would be like a kind of Fokker-Planck way of doing that in a much more simple context, in order to simplify. Then, if the problem is, as you know, I mean, to simulate the Fokker-Planck is a nightmare. But,
sure.
But from a theoretical point of view, it makes absolutely sense.
Because you imposed a detailed balance. Detailed balance is stronger condition than stationarity.
Yeah.
And
equilibrium.
That's it. So I think you can go even further with this by giving up detailed balance and looking at stationary problems. But this is technical. We talk about this later.
Well, you know, the standard trick in non-equilibrium thermodynamics is you go always in the tail balance. This is what we call quasi-stationary ansatz. And so that you are always in the tail balance, but you are moving this in time. But it's a little bit different because here we are interested in the non-tail.
One last question, if I may. Irreversibility in epilepsy. You think, I mean, there are many phenomena in epilepsy which are highly reversible.
It's related actually with they're going hand by hand with the question of turbulence. It's much easier to measure. So what we are doing actually with the people here, with Rocamora, the Hospital del Mar, is in windows of the SAEEG, to do this trick with the cheap version of reversibility, because our intuition, actually my intuition, is that the level of structuration, so of hierarchy, should change. I think should increase, but
Increasing.
this is now beer talk. I mean, should increase before the epilepsy. So it could be a good biomarker, but we don't know. we are just playing around, but it's so easy to calculate that it costs nothing.
Yeah, we can try that.
I want to briefly mention regarding this topic because in the 80s, in the 90s, some people in the context of epilepsy, they use this type of cheap version changer, comparing the model of forward in time
And backward.
with the autoregressor calculated with the shifted code.
It's this idea.
So the prediction is clear. And there are evidence of non-linearity.